Number one. Gases generally have what? Well, we know that the difference between a gas, a liquid, and a solid has to do with how close the particles are together, one thing, and whether or not particles can move. So gases tend to have lots of space between the molecules. And since density is defined by mass or volume, if we take the same mass of, say, a liquid and convert it into a gas, the volume is going to expand a lot. Rule of thumb, like 1,000 to 1. So if the volume increases a lot, the density is going to go down. That means gases tend to have a low density by comparison to other. That's why A is probably the best answer out of these. High density, no. Close packed particles, no. No increase when the volume, when temperature is increased, that's false too. We learned that with which law? Charles. Increase the temperature, increase the volume. No decrease in volume when pressure is increased, and that's Boyle's law. Actually, that's contrary to Boyle's law. All right, so A is the best answer for number one. Number two is a definition of pressure. We know pressure is a force per unit area. That's the simplest version we can put it. So which one of these would fit that? Well, D is a good answer, defined as a force per unit area. And I don't see anything else better. Measured in grams, defined as the number of moles, no. Measured in newtons, it's halfway there, right? This is newtons, this would be square meters if we're using SI units. All right, so, and the SI unit of pressure is the Pascal. So if we say, this is 3. So if we say 1 Newton per square meter, that's 1 Pascal. All the SI units are designed so they can be interchangeable. Or be not interchangeable, I should say converted. All right, number 5. A glass column is filled with mercury, converted in a pool of mercury. The mercury column stabilizes at a height of 729 millimeters above the pool. What's the pressure of the atmosphere? All right. We've got, look at the answers. They're all in atmospheres. So we've got to do a conversion. So we're saying that the atmospheric pressure gives us a height of 729 meters in that column of mercury. So we know we've got to take this one and convert it to atmospheres. So what's the conversion factor for that one? All right. If we have one, we would go millimeters of mercury in the denominator, atmospheres in the numerator. All right. Okay. So the relationship between 1 atmosphere and millimeters of mercury is 760. So divide 760 into 729, and you should get 0.959. Does that look reasonable? Yeah, this is less than that, so it's got to be less than 1. We know it won't be A. We know it won't be D. It's not close to half, so it won't be E. So you can narrow it way down to either B or C, and then your calculator breaks the tie. All right, number 6. The local weather forecaster reports that the current barometric pressure is 30.4 inches of mercury. What's the current pressure in atmospheres? All right, this is another unit conversion. inches of mercury. Now, your review document should have, let's be sure useful information has all this information, these conversion factors. Yeah. 1 atmosphere is 29.92. Inches of mercury is 1 atmosphere. So you know it's going to be greater than 1. Not much greater, but a little bit greater. And A looks like the best answer to me. Just barely over 1 atmosphere. In fact, we can see this on a really clear sunny day. You might get 30 inches even at this altitude. Remember, higher pressure signifies good weather, low pressure says bad weather. The air pressure in the inner tube of a tire on a typical racing bike is held at a pressure of 112 psi. Convert this to atmospheres. So it's another conversion, 112 pounds per square inch. So we just need something that goes from pounds per square inch to atmospheres. Yeah, atmospheres. You can look it up, and it should be 14.69. Now, my bicycle didn't have that much pressure. I think mine was 85. But racing bikes do. I mean, the narrower the tire, the higher the pressure. So their tires are about like that. And I think mine was closer to like that. But it was still difficult to get there. You know, it took a lot of work to get that much pressure in the tire. If you didn't have access to a tire pump, mechanical pump. So the best answer to this one is 7.6. Now, that makes sense. Let's see. 7 times 15 would be about 308. Okay, I'll go with that. I'm just estimating to see if we're in the ballpark. Now, these following Boyle's law, I'm not even going to write those on the board. You ought to know what Boyle's law is. Pressure times volume equals a constant. So the volume of a fixed amount of gas is inversely proportional to the pressure at constant temperature. Remember, we have 4 factors that have to be known. Let's see. Let's put that one last. This is temperature and mole. To completely describe the physical behavior of a gas: pressure, volume, temperature, and moles. And if you're drawing a relationship between any of these two, the other two have to be constant. So B is the best answer to this one. Avogadro's law. Let's see. Boyle relates these two. Avogadro relates which two? That one and that. Volume and moles at constant pressure and temperature. And Charles' law, we mentioned that one earlier. That's volume and temperature. So pressure and moles have to be held constant. C is the best answer for that one. Let's see. The next one I got highlighted. Gaseous chlorine, number 15. Gaseous chlorine would be like that. Right? That's one of the diatomics. Held in 2 separate containers at identical temperatures and pressures. The volume of container 1 is 1.3 liters. And 2 is 6.0 with 6.7 moles of gas. 6.7 moles. And the volume of the second one is 2.33 liters. How many moles of gas are in container 2? Okay. This relates moles and volume, which is Avogadro's law. And you can either memorize Avogadro's law, or you can just memorize the combined law. P1 V1 over P1 N1 equals P2 V2 over T2 2. That way, if you've got volumes and you want to find moles, then these have to be held constant. You just mark those out. So there's your Avogadro's relationship there. And we know that if we're going to solve for N2, we can bring N2 over here and take N1 over there, V2 N1, and bring V1 over here. So that would solve for N2, and then we can plug in the numbers. So V2 is 2.33 liters. N1 is 6.70 moles and 1.30 liters here. So do that math and we should end up with 12 moles. Does that seem reasonable? Yeah, 2 1/3 times 6 and 6.7 is a lot greater than 12, but we're going to divide it by 1.3, so it ought to be close to 12. Yeah, it makes sense. Remember, that's the last step in problem solution. Does your answer make sense? All right, we're down to 18. Body temperature is about 309 K. 309 K. Is that right? 273, 6. Yeah. We take the normal body temperature as 37, 98.6 Fahrenheit. That'd be kind of on the low end. Maybe they took that one of those forehead scanners. They always read low. Oops. Forget about it. What's the only way to get an accurate internal body temperature without actually jamming a probe into somebody's stomach is a rectal thermometer. Yeah. I don't think they do that much anymore. You just take it somewhere else and maybe add a degree or two. Okay. On a cold day, what volume of air at 276 K? So this is the first temperature. This is the second temperature. Must a person with a lung capacity of 2.2 liters breathe in to fill the lungs? So where does the 2.2 liters go? Which temperature is it associated with? Body temperature. So V1 would equal 2.2 liters. And the unknown is what volume of air at this temperature do you have to draw in to meet these conditions? Okay. So this is Charles' law. You just set up, let's see, if we solve, I'll just do this. V2 over T2. So we're going to solve for V2. That means V1 T2 over T1. Now we just plug in the numbers. I like to extract from the problem and put it in a form that I understand. And then I can relate it to the problem solution. And that way I don't put numbers in the wrong place. Because it's easy to get confused if you try to go straight from the words into the formula. So this would be V1, 2.20 liters, and T2, 276. And the temperature is already in Kelvin. If it were not in Kelvin, we'd have to change it. And then T1 is 309. Okay. And if we do our math correctly, we should end up with it's 18. We should end up with 1.97. So we draw in this much cold air, it expands to our body temperature to make up a higher volume to fill our lungs. Now this is about 2/3. That's reasonable. Of 1820. Scroll a little bit. Okay, holding two balloons, an orange and a blue balloon. I don't think the color really matters. This is orange and blue. Okay. The orange balloon is filled with neon. And the blue balloon is filled with argon. Okay. The orange balloon has twice the volume of the blue balloon. All right, so let's be realistic here. Reduce that volume. So this one's twice as big as that one. So this volume, the volume of the orange is twice the volume of the blue. That's what they're saying. And which of the following best represents the mass ratio? So a mass of neon ratio to the mass of argon. All right. What did they not say that we have to assume? We have to assume that the temperatures are constant. We have to assume that the temperature of the orange equals the temperature of the blue. Otherwise, we've got an uncontrolled variable and can't solve the problem. So that covers volume, temperature. Oh, we have to assume pressure also. So now we can say something about the relationship of volume and moles and relate that to mass. Okay, so what's the relationship of moles in each one? Well, if this has twice the volume of that one, then the moles of the neon are twice the moles of argon. Okay. Now, how do we relate that to mass? Well, if you've got twice as many moles of argon, what is argon's mass? About 40, roughly. So 40 atomic mass units. And neon is about 20, isn't it? Yeah, 20 atomic mass units. Or 20 grams per mole. And 40 grams per mole. But this has twice as many moles. Let's do it that way. 20 grams per mole for the neon and 40 grams per mole of the argon. Well, we're relating number of moles. This has twice as many moles as that. So if this represents 1 mole of gas, it's 40 grams. That means this would have to be 2 moles, right? So 2 times 20 is 40. Their masses are equal. It's a 1-to-1 relationship. Okay. Let's see. We'll skip a few repetitions. 29. Probably get a little weak. This one. A gas sample is heated from -20 to 57 degrees, and the volume is increased from 2 liters to 4.5 liters. If the initial pressure is 1.14 atmospheres, what's the final pressure? All right, we've got more than 2 variables going on here. So we need the combined gas law. We're going to be using P1 V1 over T1 N1. P2 V2 over N2. And we have the T1 is minus 20 degrees C. So we know we're going to have to change that one. And the T2 equals 57. Okay. How about 2 liters to 4.5 liters? So it went from this temperature at 2 liters. How many zeros? 2 zeros. To this volume, which is 4.5 liters. Okay. And the pressure, the initial pressure is 0.14 atmospheres. So the first pressure is 0.14 atmospheres. And this is our unknown right there. So what we're saying is these two are equal. So all we need to do is solve that equation for P2. So if we leave P2 on one side, that means that P1 V1 times T2 over, bring this one over here, V2 T1. But these have to be changed. So we got to add 273 to this one and 273 to this one to equal Kelvin. All right, this would be 253. Okay. And this would be 330. Okay. Okay, now we can plug our values in. P1 is 0.140 atmospheres. I'm leaving the units out because run out of boardroom. Let's get weak too. Go this one. And then P1 V1 is 2 liters. And then T2 is 330 K. And then V2 is 4.5 liters. And T1 is 253. There we go. And if we do our math correctly, we should end up with 0.0811 atmospheres. Okay. 3 significant figures. Extra, yes. Okay. We might be able to use this one again. We'll leave it up there anyway, just in case. Number 30. A sample of oxygen gas has a volume of 1.72 liters at 27 degrees and 800 torr. How many oxygen molecules does it contain? Okay. We don't need this one. 29 was a before and after situation. 30 is a state function. What is it right now? So that means we need a different formula. We need the ideal gas equation. Okay. So pressure is 800 torr. That's pressure. Volume is 1.72 liters. Okay, that's good. This one has to be changed. to give us atmospheres. Why? Because R is 0.08206 liter atmosphere per mole K. That tells you the units that you need in the other variables. Okay, numbers. So N is unknown. And T is 27. 27 plus 273. So that's 300. Okay. And this, work this one out. 800 divided by 760 is 1.053. I kept an extra decimal, so avoid rounding errors. This is atmospheres. So we got atmospheres, liters, K. So our answer will come out in moles. Now that's not the final answer because the question is numbers of molecules, right? So we solve for moles. That's PV over RT. So pressure is 1.053 atmospheres. Volume is 1.72 liters. 0.08206. And temperature is 300. That's going to give us moles. Go 8206, 300. So this is 7.354 times 10 to the minus 2 moles. Now we got to convert that to numbers of molecules. What's the conversion factor for that? Molecule. Silence is deafening. Avogadro's number. 6.022 times 10 to the 23rd. Okay. Times actually is per mole. So 6.022 exponent 23 times. And let's see. 3 significant figures. I get 4.43 times 10 to the 22nd molecules. Okay, that's why the answer is A. Okay, so it was multi-step problem. Okay. Here it is. Which conditions of pressure, temperature, and moles respectively are most ideal? Pressure, temperature, moles. And we're looking for ideal conditions. What do we mean by ideal? The gas stays a gas all the way down to absolute zero. Doesn't matter the pressure or the temperature, still a gas. And there are other behaviors that signify ideal behavior, like the molecules don't interact. There's lots of space between them. They're moving very fast and they're random motion. So which would give us that? Low pressure. Low pressure means big volume. High temperature. High temperature means lots of kinetic energy in each of the molecules. So if they do impact each other, they're not together for very long. And the energy of impact is so high that any interaction that they might have between each other is minimized. And then low moles. These two kind of go together. Low pressure and low moles were sort of given. But E would be the best one for that one. Low pressure, high temperature, low moles. 40. A 41.1 gram sample of neon gas exerts a certain pressure in a container of fixed volume. What mass of argon is required to exert half the pressure at the same conditions of volume and temperature? Okay, let's see. Volume moles, temperature moles, temperature moles. And we've got a 41.1 gram sample of neon mass. 41.1 grams of neon. Let's see. Neon. What mass of argon? Mass of argon. So that's our question. Would exert half the pressure at the same conditions of volume and temperature. So the volume and temperature are held constant. And if we wanted half the pressure, so the pressure of argon is half the pressure of neon. Okay, that's given. All right, so what we're looking at with volume and temperature fixed, the effect is moles. We want to see how many moles of argon would it take to exert half the pressure. Okay, so if 41.1 grams of neon is about, well, it's about 2. Well, we could do it exact. Maybe we better. Let's get an exact. 20.18. That 20.18 grams per mole. So that'll give us the number of moles number of moles of neon. .04 neon. Okay, so if we want argon to exert half the pressure, we need half the moles, because these two are constant. So if we want half of this value, we got to have half of that because they're directly proportional. Okay, so what we need is 1.02 moles of argon. We can convert that to grams. Moles on the bottom, grams on the top. So argon is going to be 39.95. And that's 4.0. No, sorry, not 4.0. 40.7 grams of argon. There we go. E. All right, let's see. Let's skip. Okay, for the following questions, 46 through 51, these conditions prevail for helium, chlorine, methane, and ammonia, each at 0 degrees and 1 atmosphere pressure, which means standard temperature and pressure for gases. So we're down to 49. Okay. Oh, well, okay. STP is 0 degrees Celsius and 1 atmosphere pressure, standard temperature pressure for gases. But we don't need to know that to answer the question. It says for which of the following molecules, for which gas are the molecules diatomic? Well, it's obvious. There's only one in there, right? Chlorine. Probably should have, a better question for that would have been to write that name out. Helium, chlorine, name the molecule, methane, ammonia, which are diatomic. Then you got to know. Right? That would be a better question. $52. The mass of 1.1 liters of gas Y at STP is found to be 6.23 grams. The density of the gas is what? Well, let's see, it's 6.23 grams, 6.23 grams. Density is mass per unit volume. Let's see if we got the data we need right now. 1.12 liters. Yeah. That's just a simple calculation. It ought to be close to 6. B, closest one to 6, 5.56. Why do we have to use such a large volume? It takes that much volume of a gas to give you a measurable mass. 53 follows with the same data set. So let's see what 53 asks. See, the molar mass of gas Y is what? Okay. We need to find out how many moles. We got the mass. If we want molar mass, we need mass per unit mole. So do we have enough information? It said it was at standard temperature and pressure, right? So the temperature is equal to 0 degrees Celsius plus 273 K. Okay. Volume is 1.12 liters. Moles unknown. That's what we're solving for. And pressure is standard pressure is 1 atmosphere. Yeah, we can find the moles. And then we can fit it into this equation. We've already got the mass. Right, we need to find the moles. So we're solving for moles out of PV equals nRT. So this is a state function. PV over RT. So the pressure is 1 atmosphere. Volume is 1.12 liter. 0.08206 for the R, and temperature is 273. Okay, so we can find the number of moles, 1.12 divided by 0.08206 and 273, which is 4. Well, actually, I got so many 9s in here, it actually rounds up to 5. 5.00 times 10 to the minus 2 moles. So we plug that in here. This will give us the molar mass, which is 125 grams per mole. Right? Is this a mystery, or are you just quiet? Kind of hard to tell. There's no response. Uh, 54 is blank, because that question turned out to be inappropriate for this chapter. 55. Argon has a density of 1.78 grams per liter at STP. Argon, density of argon is 1.78 grams per liter at standard temperature and pressure. How many of the following gases have a density at STP greater than that of argon? Okay. If density is mass per unit volume, how are we going to compare their densities? If they're all at the same temperature, standard temperature and pressure, then temperature and pressure are not variables. So the variable is going to be moles and volume, like N and V. So they're directly proportional, right? Increase the number of moles, increase the volume. If we increase the number, well, actually, we're going to have the same moles too. That's constant. So if we have the same moles with a given volume, okay, yeah, we have the same moles. All we need to do is compare the molar masses. Right? So if we say, let's say chlorine, helium, ammonia, and nitrogen dioxide, the molar mass of chlorine is 3545 times 2, which is 70.90 grams per mole. Okay. Helium is 400 grams per mole. Ammonia is 14.01 plus 3.03, which is 17.04 grams per mole. And NO2 is 14.01 plus 2 times 16, 32. And that should be 46, right? 46 grams per mole. I think. Yeah. Okay. This molar mass tells us that if we have the same number of moles of each one at these conditions, then the one that has a higher argon is 39.9, well, about 40. No, excuse me, wrong place. About 40. So the one that has a higher, let's go back to the question. How many of the following gases have a density greater than? Okay. The density would be proportional to the molar mass because we have the same number of moles of each of those gases as we do argon. So if we have the same number of moles, if we have same number of moles, but each one weighs more than argon, then that one is going to have a greater density because all other factors are equal. So this one at 46 and this one at 70 will have a greater density than argon. So that's why the answer is 2. Only 2 of them. And well, it's not compared to argon, but compared to air. Let's see, air is 79% nitrogen and 21% oxygen, roughly. Right. This is going to be 32. This is going to be 28, roughly. Right. But it's only 0.79 of that is contributing to air. Which is 22.1. And 21%, 32 times is 6.7. So that would be 8.2. So about 28.8 is the average, weighted average molar mass of air, whereas helium is 4. And so it's going to be about 7 times less dense than air. That's why you can fill a balloon with helium and you head for this outer space. Well, you can only get into that stratosphere and then things kind of even out. All right, 56. Okay, one more time. 1:45, less than a half hour. All right, which of the following is the best qualitative graph of pressure versus molar mass of a 1 gram sample of different gases at constant volume and temperature? Okay, so we've got a number of different gases with different molar masses, and we're plotting those against their pressures. All right, so if the molar mass goes up, we should have fewer moles of gas, which means the pressure would go down. They're inversely proportional. Okay. So let's see, what we're given is we're plotting pressure versus molar mass. I'll just abbreviate it, molecular weight. And molecular weight is composed of mass per mole. Okay. The mass is constant. Mass is constant at 1 gram. Okay. So if we say various molecular weights, say we have molecular weights that are, say, 10, 20, 30, 40, just for argument's sake, then as the molecular weight goes up and it's 1 gram, then what happens to the number of moles? If this is grams per mole, and the grams are constant, then as we go up here, then the number of moles goes down. So as this increases, the number of moles increases the other way, or it decreases. So the relationship is inverse. And what we've learned from Boyle's law is that inverse relationships are always the products equal to a constant. So we would say something like pressure times molecular weight is equal to a constant. And we know from experience that the plot of that graph is a hyperbola. It's like Boyle's law. None of them are like that. We got one with a negative slope, but it's a straight line. Close, but no cigar. That means that none of these properly represents that qualitative graph. 58. Given this reaction, let's see, 2 ammonias plus how many chlorines? 3 chlorines yields nitrogen plus hydrogen chloride gas. Okay, let's see, is that balanced? 2 nitrogens, 6 hydrogens. Yep. 6 chlorine. Yep. Okay, we're balanced. All right, what's the question? You react 5 liters of ammonia with 5 liters of chlorine. Okay. Measured at the same conditions in a closed vessel. Calculate the ratio of pressures in the container. Final pressure versus initial pressure. This is what we're after. Final pressure versus initial pressure. Okay. I don't want to make this one too complicated. I get the feeling that it's not that complicated. The number of moles on, well, since we're given exact amounts of each one, that means that one of them's going to run out. Yeah, one of them's going to run out. What's the ratio between the two? Which one's going to run out? Well, the moles are related to the volume because all the other factors are equal. So that means that we need, for every 2 of these, we need 3 of those. That means since they're equal, this one's going to run out. This one is limiting. Okay. So what we need to do is say, all right, since they're all gases and the volumes and the moles are related, right? They're proportional. I know I've said before that you have to convert to moles before you can go anywhere. Well, if they're proportional to moles, then we can still go. So if this is 2, this is the limiting one. Okay, so this is 3. How many of these will it produce? Right, what's the ratio? Right, starting, you're getting rid of 3 and you're going to 1. So a third of that. What's a third of 5? 5/3. So 5/3 liters of this will be produced. How much of that will be produced? Well, it goes from 3 to 6, so twice as much. So we get 10 liters of this. Right? So far? Okay. Well, how much of this do we have left over? Well, the ratio here is 3 to 2. So here the 5 is, this is 5 ammonia. And this relationship is ammonia to chlorine. This is 3, this is 2. Right? No, that's not right. Because we're going backwards. We're going from 5. How much of this will you need? So this is chlorine here. These have to be switched. There we go. So 2 into this is 2.5, and 2.5 times 3 is, well, that's not going to work. Maybe I had it right the first time. Oh, there you go. Is that good for everybody now? Okay. 2/3 of 5. So that's 10/3. Or 3.333. So that's how much we used. 3.333 minus 3.33. We used that one, which is 1.67 liters left over. So this is left over from excess. This is all used up. There's nothing left there. This is let's see, 1 2/3. Right? And this is 10. So the ratio of pressures in the container. So the pressures are related to moles. So the final volume in the container, this is proportional to final volume, initial volume. So the final volume is going to be 2, 3 1/3 plus 10. Okay. The initial volume is 10, correct? Because that's what we started with. We had 10 in here giving us a pressure. Then we end up with only this plus this plus this. So if I counted correctly, it's 1.33 is the ratio. Yep. See. And I know that I could just feel it. The shades coming down over the eyes and the brain going turning to mush. The point of this whole question is the relationship of pressure to volume. All of the factors being the same, as pressure goes up, volume goes up. Pressure goes down, volume goes down. The relationship between pressure and volume is the same as moles and moles. That's why we could move throughout this equation. Since they're all gases, we could move everywhere with volume, and we didn't have to convert to moles. Okay. To answer this particular question, other stoichiometries would require that we convert. Or we do this work first, and then we can convert. Okay, number 61. 15 minutes. When 0.72 grams of a liquid is vaporized at 110 C in 0.967 atmospheres, the gas occupies a volume of 0.559 liters. The empirical formula of the gas is CH2. What's the molecular formula? Okay, we know if the empirical formula is CH2 is the empirical formula, then we need a multiplier. And the empirical weight, we just go ahead and calculate that, is 12.01 plus 2.02 for the two hydrogens. 0.4 is grams per mole. What we need is to calculate the molar mass, the actual molar mass for the gas. So that's mass per unit mole. We have the mass, 0.72 grams already. We need the moles. So do we have what we need? N equals, do it this way. N equals PV over RT. Okay. Do we have the pressure? Yeah, 0.967, 0.967 atmospheres. Volume in liters? Yeah, 0.559. R is a constant. And temperature, 110 C. We have to convert that to Kelvin. There we go. So that'll give us the number of moles. Five, 9, 0.08, 06, and 110 plus 273. Divide that into it. So I get 1.72 times 10 to the minus 2 moles. So we can put that up here, 0.72 times 10 to the minus 2, and divide that into 0.72. And I get 41.9 grams per mole. So our conversion, our N, our multiplier, is just the ratio of these two, which is about 3. Right? If that's equal to 3, then we have C3H6 is our formula. Okay. I still got a few more minutes. That went faster than I expected. We're skipping a bunch of repetition. Huh. Oh, there we go. Number 80. If M is the molar mass, R is the gas constant, T is the temperature, P is the pressure, which of the following expressions represents the density of the gas? Okay. We're including molar mass. So we know that it's M equals molar mass, which is mass per mole. PV equals nRT should also come into play, gas law. And then density equals mass per unit volume. We want an expression that solves for this one. So we can solve this one for mass. Mass equals density times volume. And substitute in this one, density times volume for mass. Then we need moles. So N equals PV over RT. We can substitute in here. So this one substitutes here, and this one substitutes there. So that gives us PV over RT is equal to molar mass. Okay, so let's solve this thing. Remember, the denominator of the denominator is the numerator. So this flips, and that puts dV RT over PV. Okay, that might not get us where we want to be. Because I got a factor in here that I can't get rid of. Let's back up and look at it again. Density is mass per unit volume. Okay. Should have worked. I know this part is right, substituting that. Well, let's see, what would that leave us with? Density RT over P. Oh, I'm solving for the wrong thing. Right? We're solving for density. Okay. Well, this is good so far. Let's keep density over here. Density on one side, then M times P, and then RT comes over here. Okay. Yeah, I was answering the wrong question. It helps to read the question. So MP over RT is A. Okay. Let's see, 81. Yep, we got a little time. So we can get 81 locked out. One of the ways to isolate metals from their ores is to react with a metal oxide with carbon, as shown in the following. So we got this equation, some metal plus oxygen. We react it with carbon, and we get this metal plus carbon dioxide gas. Now we have to assume that with this equation, the creator of the equation has said that the molar ratio of oxygen to the metal is 1 to 1. 1 mole for metal, 1 mole of oxygen in this compound. Otherwise, it won't balance. So if 34.08 grams of metal oxide, 34.08 grams of metal oxide react with excess carbon, okay, and 4.37 liters of CO2, formed at 100 degrees. So this is volume, 100 degrees C. We know we're going to have to change it at that temperature, and 1.5 atmospheres of pressure. Then the question, what's the identity of the metal? Well, in order to identify the metal, there's no way we can get at the atomic number, not with this data, but we can get the molar mass, and the molar mass is increases along with the atomic number. So if we can find the molar mass, we can probably pin down what metal it is. Okay, so if we want molar mass, we need mass per moles. How many moles is that? Does this mass represent? Well, if we can find the moles of this, then this will be twice that number. And that'll give us the moles. Okay, so looks to me like we have a state function here. And the number of moles is pressure, 1.50, volume 4.37 liters, gas constant 206, and temperature 373. Okay, so the number of moles is number crunching time. Zero 0.2142 moles. Okay, that means this is the moles of CO2. So the moles of MO, well, hold on a second. That's going to give us the molar mass of this compound. Okay, let's go ahead and get the moles. The molar mass of this compound, or the moles of this compound, will be twice as many as that, because this is 1 to 2. So that's 0.4284 moles. This is 0.4284 moles. And okay. If we have a total mass here of 34.08 grams for that compound, what percentage of that compound is due to oxygen? That's the question. Well, we don't know the total. We know this value right here. So how many moles would be attributed to oxygen? Well, half of those moles, right? If this is the total moles, actually the same number of moles, look, it's 1 to 1. We have this many moles of MO. How many moles of M do we have? We have that many moles of M. What we don't know is what's the mass difference. All right. I'm making this harder than it needs to be. Are you looking at my work problems all along? Okay. What's the next step?
We're going to divide the 3408 from the 0.4284 is what it's saying.
I divide this one by that value.
Yeah,
Okay. Okay, that would give the molar mass of this compound, wouldn't it? Okay, I'll go with that. So if I divide by 0.4284 moles, grams per mole. That's 79.55 grams per mole of MO. Right? So now I need to know, oh, yeah, it's simple. This part of the molecule is 16, so the rest of it is M. So if we subtract the contribution of oxygen, 55, 83.55 grams per mole, is the molar mass of M, right? If this is molar mass of the total, then we know how we got there before, right? We just add the molar mass of that one to that one. In this case, we're going to subtract that one. This is the molar mass of oxygen. So 83.55 is, oops. Did I do that right?
you add them.
Oh, I added. My own worst enemy. 63.55. See, it can't be krypton. Here we go. Copper. That's copper. Okay. I'm satisfied. Again, number 82. The standard temperature for gases. And 83 is the standard pressure. So when you see STP, or standard temperature and pressure, for gases, the standard temperature is 0 degrees C, or 273 K. And the standard pressure is 1 atmosphere. Okay. That's just for these gas experiments. Later on, when we talk about standard temperature for any chemical reaction that's being studied, it's 25 degrees Celsius. But for these gases, it's 1 atmosphere and 0 degrees Celsius. Let's see, that's just for 84 and 85, so 86 is independent. All right, a 142 milliliter sample of gas is collected over water at 22 degrees and 753 torr. What's the volume of the dry gas at standard temperature and pressure? The vapor pressure of water at 22 degrees is 20 torr. All right, this is one that it helps to draw a picture. So collected over water means that our collection vessel, and I'm going to use for measurement purposes, I'm going to use a graduated cylinder. So we got water here, and we got our graduated cylinder. It's like this, like that, that. And it's got volume markings on it. All right, now inside the cylinder, it's completely filled with water all the way to the top. And our reaction vessel over here generates gas. Right, and it collects at the top. And that way we can measure it, measure the amount of gas produced. But the fact that it's being bubbled through water means that it's not just the pure gas from the reaction, it's also got water vapor in it. So what we do is we use Dalton's law of partial pressures. That means that the pressure of the atmosphere on the outside bearing down here and being balanced inside the container is 753 torr. Right? That's the total pressure. Okay. The volume that's collected, let's see, let's move it down some. It should be collected actually right here. So the pressure inside and outside is the same. The volume needs to be the level with this. So this is 100 and where was it? 42. 142 milliliters. The vapor pressure of water at 22 degrees is 20 torr. So the pressure inside this container, this is equal to the pressure of our gas plus the pressure of water vapor. So if this value here is 22 torr, then the pressure of the gas inside that container is equal to 753 minus 22, which is 731 torr. Okay. Now we know what the pressure is for the gas. It's this value right here. We know that the temperature is 22 degrees. Plus 273 equals 295 K. We know the volume is 142 milliliters, which is equal to 0.142 liters. Okay. What's the volume of the dry gas? Well, okay. Actually, I'm making it more complicated than it needs to be. The total volume is 142, but that volume is made up of two gases. Milliliters equals volume of water vapor plus the volume of the gas. And the ratios here, volume ratios are equal to pressure ratios. So if this is the total volume, then it corresponds to a total pressure of 753 torr is equal to pressure of the gas, which is 731 plus 22. Well, that's backwards. 22 plus 731. Okay. So the ratio, the amount of volume of the dry gas, you should be able to calculate that from the ratio here. So the ratio of the dry gas here is 731 to 753. And that's equal to the total volume in the denominator. And then this is the volume of the dry gas. So let me see if that works out. It gives us the correct answer. I think I'm working it differently here than I did in the worked problems. 731, 753, and 142. So I get 138 milliliters for the dry gas. Right, well, none of these. Right. Let me see how I worked it in the work problems. This is number 86. 28. Did I calculate that right? Where's my, here it is. Let me see if I did that correctly. Because the way I worked it in the work problems, it says 128, which is none of these also. But let's see. 142 is the volume of water, volume of gas. 753 is the total with 22 for water and 731 to, okay. So the ratio of the volume of the gas to the volume of the total is the same as the pressure of the gas, the pressure of the total. So 731, 753 should be the correct ratio. And then the ratio of the volume of the gas to the volume total should be the same ratio. So let me be sure I calculated that correctly. 731, 753, 142 is 138. Okay, now how did I get 128 from here? 86, yeah, 86. Oh, okay, okay. Oh, I put the wrong number in. This is 20. This is 20. So that needs to be 3 at 733. That's correct, although I didn't use it. So that's 733 here. And 753, this is 20. So this is 733. Okay. That's still not going to get me close to what I expected. 733, 753 divided 142. Is 142 correct? Yeah, 142 is the sample of gas. So that's still 138. Okay. That's one way to work it, and apparently I get the wrong answer. So instead, we're going to use temperature Oh, the temperature did change, didn't it? No, it didn't change. Well, how does that? No, you know what? I think I worked it wrong in the worked problems. Oh, no. Okay. That's wrong because the temperature did change. All right, let me erase this and make room over here. All right, let's put our values up here. Initial temperature, pressure, volume. Moles are going to be the same before and after. And then final, pressure final, volume final. Okay. All right, so the initial pressure of the gas is 733 torr. Yeah. The final pressure is atmospheric. Standard pressure, 764. Okay, now we're getting somewhere. Oh, shoot. This is pressure. Pressure. So that makes this temperature. Okay, the initial temperature is 22 degrees. Right? 22 degrees initial. The final temperature is 0 degrees. So that's the plus 273 and plus 273. So this is 273 K and this is 295 K. The initial volume is 142 milliliters, which is okay. We can leave that the way it is. And we're looking for the the final volume of the dry gas. Okay. Now what we have is need room. So we need P V over T, initial, and final, like that. And we're looking for this one right here. So that means PI VI TF over TI PF. Now we can plug the values in. This is 733. This is 142. This is 273. This is 295. Okay. And this is 760. Now we can get the correct answer. 733, 142, 273, 295, and 760. So I get 127 milliliters is the final volume. And it's not up there. Okay. All right, took me long enough. Dancing around the barn. Just read the question and answer it. All right, 88. Go. Let's see, I need to move that a little bit. There we go. 88. Oxygen gas generated by the reaction 2-KClO3, potassium chlorate yields potassium chloride plus oxygen. Yes. These are both solids. Okay. It's collected over water at 27 degrees in 1.55 liter vessel at a total pressure of 1 atmosphere. Okay, so again, we've got this over water. We got a vessel of some kind, and we're collecting the gas from our reaction. This has potassium chlorate in it, and it's generating oxygen gas. Okay. 27 degrees is the temperature, 1.55 liter vessel at a total pressure of 1 atmosphere. So it's 1 atmosphere pressure and 1.55 liters is the volume. The vapor pressure of water at 27 is 26 torr. So pressure of water equals 26 torr at this temperature, 27 degrees C. Okay, that's everything that's given. How many moles of KCl3 were consumed in the reaction? What we need to do is find out how many moles of oxygen are there. Well, if the pressure is 1 atmosphere or 760 torr is total, then the pressure of oxygen in that container has to add to it 26. So the pressure of O2 is equal to 760 minus 26. Be sure I get my numbers right. Minus 26 torr, yes. Okay, so that's 4 and 2 from 5 is 3, 730 torr. Well, we're going to need this in atmospheres because we're going to use PV in RT to find out how many moles. So we just divide this by 760. And that's the case. Calculator. 734, 760 is 0.9658 atmospheres. So we need that value. We need this temperature plus 273 equals 300 K. Need that temperature. We've got pressure, temperature, volume. Now we can calculate moles of oxygen produced. So the pressure in atmospheres is 0.9658. Volume is 1.55. R is 0.08206. And T is 300. Okay, so that'll give us the moles of oxygen. Let's see, 1.55 and 0.08206, 300. So that's 6.08 times 10 to the minus 2 moles of oxygen produced. The question is, how many moles of KClO3 were consumed? Now it's just a simple matter of unit conversion. O2 versus KClO3. Well, the ratio is 3 to 2. So 2/3 of that value is 4.05 times 10 to the minus 2 moles. Oh, standard notation. Okay, let's put some zeros out here. Move it 2 places. 1, 2. 0.0405 moles. That's C. Okay. All righty then. It's 88. Who's next? How about this one? There we go. That's good. 94. So we've got a 3-liter bulb and a 2-liter bulb. 3-liter bulb connected by a valve with a 2-liter bulb. Okay. Let's see, we got extra zeros in there. There we go. A 2-liter bulb in which the gas pressure is 1.8 atmospheres. 2-liter is 1.8 atmospheres. Okay. And a 3-liter bulb in which the gas pressure is 3 atmospheres. All right. What's the final pressure in the two bulbs? Temperature remains constant. So this problem requires that we think abstractly. In other words, we solve the problem by finding out what's the pressure in the system if there's nothing here on this side. It's a vacuum. And then we go and say, what would happen though if this were a vacuum and we open the valve? And we get a contribution of pressure in the whole thing from this side and a contribution from that side. And then we use Dalton's law to add them together and find the total. So we need pressure volume. Let's see. Let's say this is 1 and this is 2. So P1 V1 equals P2 V2. Well, for this side, we're going to say that one's 0. It still has 2 liter volume, but there's no pressure in it. Right? So this is going to be pressure 1 is 3 liters, 3 atmospheres. Volume 1 is 3 liters. Pressure 2 is unknown. Volume 2 is what? Well, once we open that valve to this side, and that's a vacuum, then we're using 3 liters and 2 liters. So this is 5 liters. So P2 equals 3 times 3 is 9 minus 5. Equals the pressure. 1.8 atmospheres. Okay. That's if we go from this side. If we go from this side, now the beginning pressure is 1.8 atmospheres. And the beginning volume is 2 liters. This again is the pressure if that's a vacuum. And the final volume is still 5 liters. Okay. So if we multiply these two together, we get to 3.6 divided by 5. Right? Is 0.72. So P2 equals 0.72. The total pressure is equal to pressure from number 1 in a vacuum plus number 2 in a vacuum. So the total pressure is 1.80 plus 0.72, which is 2.52 atmosphere. Okay, that's C. Okay, scroll down to 95. The partial pressures of methane, nitrogen, and oxygen in a sample of gas were found to be 135, 508, and 571, respectively. Calculate the mole fraction of nitrogen. All right. One thing we've learned is that the mole fraction of any gas, in this case nitrogen, is proportional to the pressure fraction, pressure of nitrogen over the total pressure. Actually, it's exactly equal to that. All other factors being equal, the pressure of nitrogen in that container is proportional to the moles. So we ratio the pressure to the total pressure, we get the mole fraction. So nitrogen is The second one, 508. And then the total is 508 plus 135 plus 571. That should give us the mole fraction of nitrogen. 508. And then 135. And 571 and divide. So I get 0.418. C, that's the mole fraction. And that's a dimensionless number, right? Because millimeters of mercury on the top and the bottom cancel. Right? It has no dimensions, which can be dangerous unless you know exactly where it came from. If we identify that as the mole fraction, then we know that this is applied to nitrogen versus the total. Dalton's law of partial pressures, just memorize the definition. That's the total pressure of mixed of gases is the sum of the partial pressures of all the gases. And then there we go. We got another one. 103. Calculate the root mean square velocity for O2 molecules in a sample of O2 gas at 11.8 degrees C. All right, go to your useful information and you'll get the root mean square velocity. Mean square. I think they use a U. Is equal to the square root of let's see. I have to look it up myself. Um, 3RT over 3 times R times temperature over the molar mass. I'll say molecular weight, molar mass. Okay. The trick to this one is be sure and use the right units of measure here. Because if we've got a square root of 3 times 8.3145, this is joules per mole K. And joules is based upon international standard units, kilograms. That means the molar mass and the temperature, of course, which would be, let's see, what was the temperature? 11.8 C. 11.8 plus 273. Okay. Divided by the molar mass has to be converted to not grams per mole, but kilograms per mole. So oxygen O2 would be 32 grams per mole. And I just say, if we're going to convert it to kilograms, we have to say 32 times 10 to the minus 3 kilograms per mole. Because that's 1,000. A gram is 1,000th of a kilogram. So that's what this term is for right here. All right, this goes in here. 3. And notice I don't have to put it in scientific notation because my calculator will accept exponential notation like that. So let's say 3 enter 8.3145 times and 11.8 plus 273 times, and then divide by 32 exponent minus 3. So the velocity, the root mean square velocity of oxygen under those conditions is 2.22 times 10 to the 5th meters per second. I did that right. I got 471. Okay, I did something wrong. Let me see what it is. Oxygen gas. 3RT. Okay. Divided by molar mass. Molar mass is 32. So this should be. Yeah, that's right. Kilogram would be 1,000 times that. That would drop out 32. Okay. Let's see. Did I do the calculation correct? Oh, I forgot one important step. The square root. So let me take the square root here. Okay. Square root of that. That equals 4.71 times 10 squared, or 471 meters per second. Details. Details matter. C is the answer. Okay, 109. Which of the following is included as a postulate in the kinetic molecular theory of ideal gas? Well, let's see. The distance between gas molecules is small compared to the size of the molecule. That's false, right? A is false. The distance between molecules is huge compared to the size of the molecule. B, all collisions between molecules are elastic. What does that mean? We didn't use that term in the lecture. Elastic means conservation of energy. In other words, there's no energy lost in the impact. Or as they come together, bounce off, they got the same energy going as coming. So B is correct. 100% elastic collisions. And C, in an average collision between molecules, both molecules have the same kinetic energy. No, they don't. They don't have to. They can be traveling at the same velocity, but they might have different energies because they're different sizes. Right? So C is false. D, all the molecules are move randomly in zigzag directions. Okay, if they'd have stopped it randomly, it would have been correct. But zigzag, there's no way to tell, right? It could travel in a straight line and bounce straight back, right? That's not zigzag. So all you need to do, all you have to do to disqualify a statement is to find one exception, and we found one exception. So D is false. All molecules have the same velocity. Nope. Now, hold on a second. If the temperature is a measure of the average kinetic energy of all the molecules in a container. So if we take the temperature of the container before it reacts, then all the molecules will have the same average kinetic energy. Okay. In an average collision between molecules, I'm looking at C again. Both molecules have the same kinetic energy. No. They have a distribution of energies. So if this is the energy scale, and this is the number of molecules, then they would generally have a shape like this. Most of them would be in this range, but they wouldn't be the same. Some of them will be out here, some of them will be over here. So that's the key to C being false, is the same kinetic energy. No, they have the same average kinetic energy for the whole group, right? But they don't have the exact same energy. Both molecules don't have the same energy. All right, so we were correct initially. B is the only correct one in there without any qualifications. Let's see, 111, Graham's law. All right, let's see, I think there's a mathematical expression for Graham's law, which is let's see, what did I mean by that? Energy of I think it's distance traveled. ERA. So I'm going to say distance for molecule A related to distance for molecule B is proportional to the square root of the molecular weight of B divided by the molecular weight of A. So they're inversely, this ratio is inversely proportional to the square root of the molar masses. Yeah. Okay, I know what ER means. ER for A, ER for B, and your useful information, that means effusion rate. So the rate for A compared to the rate for B of movement of the molecules. So if you measure the distance traveled over the same time interval for both of them, then the time interval drops out, and now you're talking about distance. But the exact value is the rates of effusion of gases are inversely proportional to the square roots of their molar masses. That's what this says right here, here and here. That's Graham's law. 116. Hydrogen and chlorine gases react to form hydrogen chloride. You and a friend on opposite sides of a long hallway, you have the hydrogen and your friend has the chlorine. You both want to form hydrogen chloride in the middle of the room. Which of the following is true? So we look at our choices. When do you release the gases? All right. Well, Graham's law says that hydrogen gas will move faster than chlorine gas because of the mass difference. This is 2.02 grams per mole. This is 70 point, let's see, 35, 45, 90 grams per mole. So if the hydrogen is going to move faster, this is your long hallway, right? And let's see, who's who? I've got the hydrogen, so this is me. I've got the hydrogen. And this is my friend who's got the chlorine. Okay, we want them to meet right in the middle. Okay, so which one releases first? The one that moves the slowest has to release first so that it has time to get to the middle before the hydrogen does, or at the same time the hydrogen does. So this is release early, and this is release late. Chlorine has to be released first because it moves slower, according to Graham's law. So B, your friend should release chlorine first. That's the one. Okay. How about 117? Order the following increasing rate of effusion. So we want to order them by which one goes fastest. Oh, increasing rate, which one's slowest to the fastest. So since they're inversely proportional to their molar mass, the slowest one is going to be the heaviest one. So what we need to do is find out which one that is. F2, CL2, NO2, I think, and CH4. So the molar mass of this one is 38 grams per mole because it's 19 for each one. And this one I just did 35, 70, 45, 90 grams per mole. NO is 14.01 and 16. So that's 30.01. And this one adds another oxygen on it. So it's 46.01. And this one is 12.01 plus 4.04. For the hydrogens, 16.05. Okay. From slowest to fastest, increasing rate. So the rate increases as you decrease the molar mass. Okay, what's the smallest one? 16.05 ought to be over here. Well, let's put that's methane. Methane is the fastest in terms of rate. Okay, the slowest one is going to be chlorine. Okay, then the next one is going to be NO2. Okay, we got this one, we got this one, we got this one, then F2, and then NO. Okay, so let's see which one matches that. Chlorine, NO2, fluorine, NO. A would be your answer. $118. This thing's getting kind of light. Complete the following. Because real gas particles have attraction for one another, let's see. A, real gases act most ideally at standard temperature and pressure. No, because that implies that once you've reached standard temperature and pressure, you have ideal behavior, and anything outside those values is non-ideal. So that's not right. B, we assume gas particles have negligible zero volume. Well, let's look at the statement. Because real gases have attraction for one another, we don't assume anything about their volume according to attraction. What we want to see for attraction purposes is energies. So C also says 1 mole of an ideal gas at volume at standard temperature and pressure has a volume of 22.4 liters. That has nothing to do with attraction. D, real gases act more ideally at higher temperatures and lower pressures. That's the one that overcomes attractions, high temperatures and low pressures. So D is the correct answer. $124. Of the following real gases, which would be expected to have the lowest van der Waals correction for intermolecular attractions? All right, we want gases that do not attract. Lowest van der Waals correction for intermolecular attraction. One thing we have to have is nonpolar behavior. And the other we have to have is small size. The smaller the size of the molecule, the greater the distance between molecules, plus at any given temperature, the higher the velocity. So what we want is something that's small and nonpolar. Ammonia can't be it, because ammonia is like this, right? It has this pyramidal shape, and it's polar. Right, so ammonia has very strong attractions to one another. Hydrogen, chlorine, and oxygen are all nonpolar because they're bound together, equal elements, and they share electrons equally. So there's no polar nature to any of those. What we'd see, though, is with the smaller one, you have less possibility for attractive forces because it's concentrated in a small area, and when they get close to one another, well, this is a topic we need to hold this topic till later, so just memorize the answer for this one. The attraction is based upon size. So if we have a large molecule or a large atom, the likelihood that the electrons are going to congregate on one side or the other, more often producing a slight imbalance of charge, is more likely. So the larger one, the chlorine, is a huge molecule compared to oxygen, which is also huge compared to hydrogen. The least attractive forces will be experienced by hydrogen. All right, 132. That's not working either. A manometer is attached to a sample of gas that occupies a volume of 2.34 liters. The mercury level in the arm of the manometer attached to the gas sample is 24.3 torr, lower than that of the arm open to the atmosphere. Okay, this tells us how the picture should be drawn. Manometer is a pressure measuring device for trapped gases. So if we have a gas trapped here, and we attach it to a manometer, and that's open to the atmosphere, okay? Then we're told that the volume is 2.34 liters. Well, maybe we need that, maybe we don't. The arm of the manometer attached to the gas sample on this side is 24.3 torr lower than the arm on this side. So if we have mercury this side, then the difference between the two is 24.3 torr. Okay. The atmospheric pressure is 1.23 atmospheres. That's pretty high, actually. 1.23 atmosphere. Okay. So what's the pressure of the gas, the sample of gas here? Well, it's obviously enough pressure to hold this much mercury up, plus the pressure of the external atmosphere. So the pressure inside here is equal to this pressure plus that pressure. So 24.3 torr. Let's see, our answers are in torr. 24.3 torr plus this is 760 torr per atmosphere. So we multiply 1.23 times 760 is 935. Plus 900, let's see where we got that. 35 torr. And it's 24.3 is about 959 torr. Got anything close to that? Yeah, E, 959 torr. This is the tricky part right in here, understanding how that's set up. That's why drawing a picture is often helpful. Okay, any more? Let's see, we're skipping a few. That's it.